chapter 19, slides 12 through 22. Let's now focus on some reactions of ketones and aldehydes that are new to us, namely acetals and thioacetals. The difference between what I just covered with you in review was that although R and Q are carbon or hydrogen, that's what makes them the ketone or the aldehyde, I showed you last time that the nucleophile was also a carbon or a hydrogen. What we're going to do right now is we're going to make the nucleophile something else, not carbon or hydrogen. What about oxygen or sulfur? What effect will that have? Well, you'll see that we're not going to go from our start. We're going to do the in up, but once we get to this crossroad, we're actually going to do something else. Okay, so I'm going to walk you through that. It's the what happens when the nucleophile is oxygen, sulfur, or nitrogen. This reaction, although not very useful to us, and I'll explain why, forms something called a hydrate. Now, we haven't really seen hydrates yet. They look similar. They look familiar to us, right? You have a carbon, and it's got what looks like an alcohol off of it. But it has two alcohols off of the same carbon. This is called a geminal diol, also known as a hydrate. Now, how do these form? Well, these can be formed under either acidic or basic conditions. And they do occur. They happen. Okay, this reaction that I'm going to show you will occur. However, it goes nowhere. What you should notice are the reversible arrows. So let's just consider the base catalyzed formation of a hydrate. Let's take a simple ketone and react it with NaOH. If you've ever wondered why NaOH didn't do a 1,2 addition, like why did it, do acid-base chemistry over here? Well, it probably is doing a 1,2 addition. The negative oxygen attacks the electrophilic carbon. We're showing how these carbons were electropositive. Now notice you've got a nucleophile in charge, okay? We went in and up. The nucleophile was strongly negative. You end up here, and what's going to happen? It's going to go down and out. That just takes us right back to the beginning. Effectively, hydrates are highly unstable under basic or acidic conditions, and so largely they favor the starting material. So if this is happening in solution, we at the end of the day, upon workup, once we neutralize everything, we see no evidence of it happening because all we recover are our starting materials. So I'm not saying that O- doesn't attack the electrophile. I'm just saying it happens, except it just goes in, up, and then it knocks itself back off. Same thing under acidic conditions. You just add an extra mechanistic step. If I was under acidic conditions with water, the first thing you would do, and this is going to be your knee-jerk reaction, whenever you see a carbonyl and you're in acidic conditions, I want your knee-jerk reaction to be acid-base chemistry with the carbonyl. Carbonyls react with acids. This is your knee-jerk reaction, okay? So we're first going to do acid-base chemistry. So that's what's happening here, the acid-base chemistry. Why did we need to do this? Well, is the nucleophile strong? No, it's water. It's partially negative. Remember my frat party effect? When you go to a party and two atoms are attracted to each other, one of them has to be bold enough, charged, to go and ask the other out. In the base catalyzed sense, you had a strong nucleophile, a formal negative charge. In acid catalyzed reactions, you empower the electrophile. The acid allows that to occur. That's your catalyst. So the carbonyl does acid-base chemistry to now have a very positive electrophile. And the weak nucleophile, we've been using this language all along, SN1, SN2. Now it can do the in-up. The problem is, after you do in-up, it just wants to kick the water out. At workup, it'll just do a down and out, just like the base catalyzed. And what you'll find is that it much prefers to be back in the carbonyl form. They're just not stable. So I do this exercise with you to prove a point, to show you that it is happening, because as we see other chemistry moving forward, one of the biggest questions I get is, well, why didn't it just attack the carbonyl? And I can usually point back to this slide, and I can tell you it is attacking the carbonyl. I'm not saying this isn't happening. It's going on. But at the end of the day, when you work up your reaction, you just end up recovering your starting material, so it looks like nothing happened. So why didn't I put a flashcard for this? Well, despite the fact that hydration is something that occurs and is energetically favorable, as I mention here, it's not possible to isolate these hydrates. Sometimes they're intermediates and can be further reacted in situ to form something else, but for all intents and purposes in this course, they're just unstable. And so studying their mechanism is important, but we're not going to be making hydrates as a final product. They do help us understand, though, what happens when you have certain nucleophiles that are not hydrogen or carbon. I'm going to now introduce something called the hemiacetal. Hemi means half, right? Like hemisphere. It's a word that means half. So it's a half acetal. I haven't showed you what an acetal is, but understand this is half of one. All right, we're going to form an acetal in the next slide, but let's look at a hemiacetal. A hemiacetal will do acid-base chemistry, and these are always, well, I shouldn't say always, but typically they're done under acid-catalyzed reactions. Okay, so let's start with an aldehyde, a very simple aldehyde. I'm going to react it with ethanol and acid. Okay, so if you look, we're using ethanol and it's a weak nucleophile, but we have acid here. So let's use the acid and our knee-jerk reaction for acid-base chemistry to make the carbonyl do acid-base chemistry with whatever acid I've added, H2SO4, H+, and get the electrophile to be charged. Now we can do some chemistry. We have a very positive electrophile and a weak nucleophile. We are now ready for our in-up. Now notice the difference here. Before, I was using water or OH as the nucleophile. I'm now using an alcohol. Not water, an alcohol. This is going to make all the difference. So if I had one equivalent of this alcohol, I can only do this once. The weak nucleophile goes in and up. Here's my in-up. Remember, I'm driving on. This is what I'm driving on. I'm driving on the ethanol. And if I were to work it up, at this point, I might get a little bit of this hemiacetal. So notice the carbon of interest. A hydrate has an OH-OH off of the same carbon. A hemiacetal has an OR-OH off of the same carbon. It's a half. I wonder if you can decide what a full-on acetal is. If this is half of an acetal, what is an acetal? You know that a hydrate has 2 OHs off of the same carbon. A hemiacetal has 1 OH and 1 OR off of the same carbon. Now, notice the arrows I drew. The arrows I drew favor going back to the starting material. These are reversible reactions that are governed by an equilibrium, right? Because it's all acid-base chemistry. And these hemiacetals are usually not isolatable, not stable, unless they are part of a 5 or 6-membered ring. You know where we see these the most? We see them in carbohydrate chemistry. When you go into biochemistry and you start talking about fructose, sucrose, and glucose and different carbohydrates, you talk about them being in an equilibrium in the open chain and closed chain form. So this would be the open chain, and we've been drawing them, you know, like OH and aldehyde and the Fisher projections, right? We've drawn Fisher projections of carbohydrates. These are the open chain configurations. They are in equilibrium with their closed chain form, okay, in equilibrium. What you'll see here is that the aldehyde, there's your aldehyde carbon. And here is your alcohol. It's attached to a carbon, albeit a very big carbon chain, but it works the same way under acid catalysis. The oxygen does an in and up. And what you can see is that this is the anomeric carbon. The oxygen is now attached, and it's a hemiacetal because that black anomeric carbon right here has an OR group in yellow and an OH group in blue. Technically, it's a hemiacetal. And this can go backwards and forwards, backwards and forwards. It can ring close, as I showed in the in-up, or it can reverse back under acidic conditions. If it reprotonates, it can reverse back and open back up to its open chain configuration. So these are in equilibrium with one another. So this is about the only time we see hemiacetals being able to be isolated in their 5 or 6-membered ring carbohydrate configuration. So we'll see those from time to time, but I want to use something that are far more stable. They're not super stable, but far more stable and thus more useful to us. And that's the full-on acetal. Now, it may be no surprise that an acetal is an OR group. So this is where you have, it's like a diether on the same carbon. That's an acetal. Let's work out the mechanism. Again, these will be run using acid catalyzed conditions. Let's do acetone. And I'm going to give you 2 equivalents under acidic conditions, 2 equivalents of, say, methanol. Okay, it could be any alcohol. Okay. All right, so the first step, knee-jerk reaction. When you have a carbonyl in the presence of an acid, you're going to do some acid-base chemistry. We must. Methanol is a weak nucleophile. We need to, under acidic conditions, empower this electrophile. Now, methanol is what we're going to be driving on. You'll see me using a color to keep track of. It can get kind of confusing. So keep track of what you're driving on, because remember, these are reversible reactions. I can totally drive it backwards. So in order to avoid drawing the backward arrow to show going back to the beginning, I like to highlight what I'm driving forward using Le Chatelier's principle. So I've used acid-base chemistry to empower my electrophile. I'm now ready for my 1,2 addition. Take the methanol and go in and up. I'm using reversible arrows because the atom that I'm putting on is able to come back off, right? It's not a carbon or a hydrogen. So that's how you know to use reversible arrows. It's not intuitive, like you can totally figure it out. I remember being a student and going, how do they know when to use reversible arrows and when they use the regular forward arrows? And you just have to look at the nucleophile, right? If you're adding a hydrogen or a carbon, well, you can't take those back off. Adding an oxygen, a nitrogen, a sulfur, those are going to be reversible because you can come down and out and kick those out. So just think about what you're doing. Okay, so we would just put the electrons up to the oxygen and we have OH with a methyl group there. All right. Now, highlight what you're driving on. Remember, the OH, right now it's in a hemiacetal form, right? Right now I have the hemiacetal configuration. I know this is not stable, so I'm working towards the full-on acetal. In order to do that under acidic conditions, I need the OH to go away, the blue OH to go away. So remember that we're driving the yellow methanol on, we're driving the OH off, and we're going to drive it off as water. So under acidic conditions, understand that there's acid all over the place, right? So the oxygen can grab a proton, and there's probably a conjugate base around the solvent itself that can take off the extra proton. This is called a proton shift, and you've seen them in a previous slide. They're what electron-pushing organic chemists use to shorthand in order to make things better leaving groups. Under the circumstances, we're in acidic conditions, so anything can be protonated to make it into a good leaving group. So I've got too many protons over here. On the yellow oxygen, I have one too few on the blue, so I'm writing things. I just want you to note that the hydrogen on the yellow oxygen is not the exact same hydrogen that is shifted to go over to the blue. The whole system is in a sea of solvent and acid, so it can be that proton can come from the solvent, okay? We say proton shift just to neaten things up. But don't be fooled that the yellow hydrogen is the one that's going over and shifting over. It's not like that. It's definitely intermolecular. So now we've made the blue oxygen primed to leave. And we're in position now for the methyl oxygen to use its electrons and assist. Now this is the interesting part right here. Okay, we did acid-base chemistry, in and up, proton shift. Now we're ready. You would think, oh, we just want to do a substitution. I'm going to draw your eye to the flashcard. In no way, shape, or form are we doing any SN2 chemistry here. There is no SN2 chemistry going on and to kick off that water. We're under acidic conditions. If anything, you're going to think more SN1 than SN2. Okay, we don't have a strong nucleophile. We have a very hindered carbon. There's no way a nucleophile is going to attack that carbon. So what's going to happen next is we're going to use the oxygen, the yellow oxygen's lone pair, to assist and push out. Right? So you can consider the methanol attacking as the in-up. We proton shift to get things ready, and then we do a down-out. But we don't do the down-out with the blue oxygen. We use the new yellow oxygen to assist. This now gives us the yellow oxygen. But look, we've made a carbonyl. Carbonyls are wonderful. It's an activated carbonyl too. The oxygen's positive. So we have a very strong electrophilic carbonyl species. Better yet, the carbon of the carbonyl, which it always is sp2 hybridized. So it's flat. There's no steric hindrance issues. So the next equivalent of the methanol can much more easily attack. So don't try and do an SN2 and knock the water off. Do not do that. Okay, that is not what's happening. Instead, the second methanol is now ready to attack. This gets us to the acetal, the carbon with 2 OR groups on it. Now I can work this up to neutralize the acid so that my acetal is safe. It's really just a diether. And if you remember, ethers are pretty non-reactive. So overall, what we've done is we've converted a carbonyl, like a ketone, into an acetal. And in doing so, we have stripped the carbonyl of its strong vector polarity, rendering it into a much less reactive acetal species. If you notice, all of these arrows were reversible. So acetal formation is reversible. Acetals are fairly stable under neutral conditions and can be isolated. Acetals don't behave like carbonyls. They're not carbonyls. So I want you to think of them as protecting groups. Okay? They can protect a carbonyl from reacting with something. And then when you've protected it from whatever you were introducing to your system, you can reverse it back using Le Chatelier's principle. What would you need in order to reverse it back? Have a think about it. Let me finish balancing my equation here. The workup was under basic conditions to neutralize everything. Just pluck off that extra proton. But understand that we did lose something. We lost water in the process. Right back here. That water got kicked off. So don't forget, water was lost in the process. So I'm gonna break the surprise here. I'm gonna ruin it for you. But if you wanted to go backwards using Le Chatelier's principle, I would add tons of water and some acid to go backwards to the carbonyl. The carbonyl plus acid and a lot of methanol, Le Chatelier's principle, will help me drive it towards the acetal. So you can use the Le Chatelier's principle to drive the equilibrium towards the carbonyl using lots of methanol or alcohol with a little bit of acid, or you can drive the acetal back to the carbonyl using tons of water, driving the water on, and a little bit of acid. Now, if we were to do this reaction on different carbonyls, I wanted to draw your attention to the bottom one, or the middle one, I guess. Doesn't really matter. I'm going to have you do the top two. Let me do the bottom one with you guys. All right, so the first step is acid-base chemistry. We need to empower the electrophile. Okay, done. Now we remind ourselves that we're driving the alcohol on. Okay, we're driving alcohol on in an in-up fashion. So the trend for in, up, down, out when you're doing it under acidic conditions is acid-base chemistry. In and up. Followed by acid-base chemistry. Down and out. Whenever you're doing basic catalyzed reactions, it's just in, up, down, out. But acid-base chemistry, there's like an intermission acid-base reaction you have to do in between. Remember, we're driving on this, we're driving on this alcohol. We're driving off the OH. We don't want to be stuck with a hemiacetal. So we did acid-base chemistry, in and up. Acid-base chemistry, or proton shift, right? We're going to shift the proton to make a better leaving group. OH2, because we're in acidic media. O. Let's highlight. You can see it gets messy. So highlight what you're driving off. Keep track of what you're driving on. Okay, we did acid base, in, up, acid base, down, out. Remember what you're driving off. We're going to go down, assistance, and out. I'm just going to flip the molecule so it'll be a little easier to deal with. We just got that guy on. We just lost the water. Water got lost. Okay. This is where students get confused. They're like, well, I only have one molecule of that ethylene glycol molecule, which happens to be antifreeze. And they say, well, I don't know what to do now, right? Do I add another one of these molecules on? No, you don't need to. This is the beauty of ethylene glycol. It already comes with its own second equivalent of alcohol. Look at that, it's on the other end. So that is an alcohol as well, and it's just dangling perfectly close to your carbonyl for the second in up. Isn't that just amazing? Look at that, there's your acetal. All that's left now is the workup under basic conditions to remove that extra proton, and you have just protected your ketone as an acetal using a very neat and tidy one molecule ethylene glycol. Now you might go, oh my gosh, how am I supposed to have seen that? Well, look at what you did over here. What I want you to pay attention to is that you did it intermolecularly, which I think is a little more difficult. Take a look. The only difference is that the two carbons that we're dealing with are joined. It's the only difference is that in your final product, the two carbons that you've added off of the oxygen are just tethered. Okay? So there's no mechanistic difference between adding methanol twice or using one molecule where the two methyls are tethered to one another. Okay? So ethylene glycol, one equivalent of ethylene glycol, serves as both alcohols in your system. And you end up with your beautiful acetal. Okay, I'm going to leave the others for you. Now, what reagents can we use to go from the acetal back to the carbonyl? Well, as I mentioned, we're using Le Chatelier's principle, so we've got to drive water back on. So we have our alcohols, or soon-to-be alcohols, right? Methanol will be the byproduct. And we want the water to be driven on because that's what's going to give us the carbonyl back. So I would like for you guys to see how to do this mechanism. Work this through with me, okay? I'm going to use the cyclic acetal, and we're going to add water and acid and use the same highlighting. We're driving the water on, we're driving the acetals off, okay? All right, well, we have a weak nucleophile, water, so we've got to make the acetal protonated. It was pretty much the last thing we did in the workup, right? In the workup, we deprotonated the acetal. Now we're putting the proton back on. We're literally doing the reverse reaction. Remember what you're driving off. Okay, well, do you want to do an SN2? Have we ever done an SN2 with these? No, this is all a series of in, up, down, outs. You can do down, out before you do in, up. So let's use the other oxygen to assist the leaving group intramolecularly. This is our down, out. Now we have kicked off one of the OHs of the alcohol. And we've formed a much less sterically hindered carbon. We have an sp2 carbonyl now. That's activated, positive. So now my weak nucleophile is ready for the attack. I got lots of it, so it's going to do my in and up. You're going to end up with a series of all sorts of oxygens all over the place, and it gets confusing, which is why, again, I like to highlight what I'm driving on, driving the blue on in this case because I'm going backwards. I'm driving the acetal off. Then we're going to do a proton shift, acid-base chemistry, because I want the yellow oxygen to leave happy, and I need to remove an extra proton from the water I just put on. So we're going to see to it. That my yellow acetal system is now ready to leave as a happy molecule. And my water is now deprotonated so it can use its electrons to do the final push out, down and out. And we've now put our water on. We've thrown off our ethylene glycol, our protecting group. Now this is cheap. Ethylene glycol is pretty cheap. And we just work it up to remove the extra acid, right? So we add a base, a very mild base, to remove that extra proton and give us our desired carbonyl. And that's how you remove the acetal. So remember, it's Le Chatelier's principle. Add more water with acid, you drive it towards the carbonyl. Add more alcohol with acid, you drive it towards the acetal. So what can this reaction do for us as a protecting group? Well, recall the reactivity trend for different carbonyls. Remember that acid halides are way more reactive than aldehydes, which are more reactive than ketones, which are more reactive than carboxylic acids and esters, which are about the same. And they're more reactive than amides. Why? Because the groups off of these carbonyls either donate or withdraw. In the case of a halogen, they withdraw, making the carbon more electropositive and more reactive. As you move across, hydrogen doesn't do anything. It doesn't add electron density, nor does it take away. A methyl group is a donating group, so it takes it away a little bit. Also adds a little steric hindrance. Then you move to very strong donators, like oxygen, and even stronger donators, like nitrogen, because it's less greedy. So this is the least reactive. Well, this reactivity trend isn't a bad thing. What we're going to focus on, since this is the ketone aldehyde chapter, is right here. I want you to see that aldehydes, due mostly to the fact that it has more electrophilicity than a ketone, and also, okay, I won't argue with you, a little less steric hindrance too, with a hydrogen rather than an alkyl group, aldehydes are more reactive than ketones. So what happens when you have a molecule that has both an aldehyde and a ketone present? And you want to do a Grignard. You want to add a carbon. If I look at the carbon 1, carbon 2, 3, 4, 5. Look at the products. Carbon 1, carbon 2, 3, 4, 5. There's a carbon 6 that got added to carbon 2. So you could assume that it was a Grignard or a methyl lithium, right? So if I added, let's say, methyl lithium, carbon minus. Let's say I added one equivalent because you didn't want to add it to both the aldehyde and the ketone. So if I had only one equivalent of the carbon, then which one is it going to attack? Well, if I look up at my reactivity trend up at the top here, it says that aldehydes are more reactive than ketones. So you know what? That's not going to give me the product I want. Maybe this is not how I should go about doing this. Perhaps the first step is to make an acetal with one equivalent of the ethylene glycol. I just said that aldehydes are more reactive, so it's going to react with the aldehyde first, thus protecting the aldehyde from further reactions. Then I can employ my methyl lithium, the only carbonyl that it can attack is the ketone now, and then I work it up. And then I can release the acetal by driving water back on and reforming your carbonyl. So there's a designed synthesis using a protecting group, using an acetal as a protecting group. Consider the next reaction where you have a halogen that can do SN1, SN2 chemistry and an aldehyde, and you want to see this as the only product. I'll let you guys give this one a go as a practice. Now, acetals are widely used in industry as prodrugs. Now, what's interesting, it's all about your perspective, right? The perspective that we're taking right now is that we're trying to use them to protect ketones and aldehydes. So the important part is the ketone or the aldehyde, right? And the throwaway is the cheap, it's just that cheap diol, right? It's just ethylene glycol and it's cheap and throwaway. The important part was here. We were like, oh, this is the guy we're working with here. We got to protect it. We're going to use this throwaway ethylene glycol. Well, let's just flip this on its head. What if the throwaway was acetone? It's really just your own perspective. And what we were really trying to do was protect this important molecule that had two alcohols, 1, 2 next to it. So the important keeper was the big molecule with the two alcohols on it. Alcohols are prone to acid-base chemistry. And if you have two alcohols right next to each other, you can actually protect them as an acetal using a throwaway like acetone. And that's exactly what, in this case, this drug is doing. So inactive compounds that are converted by the body into active compounds are what prodrugs are. Prodrugs are delivering a molecule to your body in a protected form, knowing that once it's in the body, the conditions in our body, maybe acidic and aqueous, will convert it to the drug that is active and needed. Why do we do this? Well, lots of different reasons. One of the many strategies, and I'm highlighting it here, in drug design for prodrugs is the use of acetal groups, because once where it needs to go, it can do the work. But the problem is that we have a lot of good barriers. One example is an acetal used in fluosinonide, I have a hard time saying this one, which is a topical treatment for eczema. Now, our skin is a fantastic barrier, as it should be, to prevent foreign substances from crossing, right? So what you've got to do is you've got to make the molecule able to cross our skin to get to where it needs to go. So the feature of an acetal protects us from the function of our skin is to protect us from harmful substances, but it also prevents the beneficial drugs from getting there as well. So to circumvent this problem, the two OH groups that I've highlighted in orange to the right are temporarily converted to an acetal in blue using the throwaway acetone that's capable of penetrating the skin. So you're taking away the hydrogen bonding capability here. So this molecule as an acetal can cross your skin. Once the prodrug reaches its target, the acetal group is slowly hydrolyzed. Our body's got tons of water, right? So if you want to take away the acetal and reveal the diol again, very, very easy. Our body can provide the acid in the water. Really cool stuff. It's like masking and then hoping that all the acid-base chemistry in our body can provide. There's examples in the literature with things like eye drops, like in order to get to where it needs to go within the eye, and then hydrolyze once there. Here's another beautiful example. Now this one uses nitrogen instead of oxygen, but I just want to direct your attention to this reaction here. Instead of using an oxygen, you can imagine that nitrogen can do the same. N has to have two groups off of it, right? So this is an aminal. And so these aminals can also be hydrolyzed if you force off the nitrogen, the NRs, and you force on the water, you can convert this aminal back to the carbonyl, just like acetals can get converted back to the carbonyl with water. Hydrolysis, right? So take a look at this very, very, very interesting kind of cagey bicyclo molecule. If you'll notice, each one of these carbons has an NR2 off of it. 2 NR2s. Each carbon has 2 NR2s off of it. See? Now, what I'm going to draw your attention to is the fact that aldehyde, like formaldehyde, has antiseptic properties. So I told you it was toxic, and it is. However, formaldehyde has been shown to have antiseptic properties that can be employed in the treatment of urinary tract infections. In fact, it's quite good at getting rid of urinary tract infections. Problem. Formaldehyde is toxic, as I mentioned, when exposed to other organs in our body. So you're trying to treat a urinary tract infection, but you can't just, down some formaldehyde or even take a pill of formaldehyde. Solution, you've got to sneak the formaldehyde into the digestive system through the use of prodrugs. And you can do this using the methenamine compound shown down here. Now, this methenamine compound, because they're just a series of carbons, it's like an intramolecular aminal, right? There's how many carbons? 1, 2, 3, 4, 5, 6. There's 6 carbons and they all have 2 H's off of it. Oops. And so they encapsulate this molecule in a pill. And the pill they design to be acid stable. So watch what happens. The methenamine is the prodrug inside an acid stable pill. You take the pill and you manage to get it through the stomach without damaging the pill because the pill is acid stable. Once this pill reaches your intestinal tract, it's under basic conditions and the pill falls apart. So now, if you'll notice, you've exposed your prodrug. It gets through the intestinal tract and dissolves the pill effectively. Now you have a free methenamine prodrug. Once this prodrug reaches the acidic urinary tract, which has water as well as acid, it completely falls apart to 6 equivalents because there are 6 carbon CH2s. It falls apart to this ammonium species, not a bad thing to have in your urinary tract, and the formaldehyde needed to get rid of the infection. That is some beautiful stuff. Really cool chemistry. All right, I'm going to show you one more heteroatom that we can add, and it's going to form an acetal, but because it's with sulfur, it's called a thioacetal. These often make 6-membered rings as their protecting group acetals. And we attribute sulfur to being yellow, so I'll continue with my trend of making the acetal yellow. And it's made of sulfur, so perfect. All right, so let's start with an aldehyde. Again, this is the ketone aldehyde chapter. Anything that I've shown you that works with a ketone also works with the aldehyde. Now, the key here is to notice that these are not reversible reactions. And this is not, again, evident by, just looking at it. You could do the math and figure out that the bonds you're making with the sulfur carbon are very strong and they don't reverse easily. So this allows us some new chemistry that we can explore. So this is a much stronger protecting group. It's more stable to multiple conditions. You know what the downfall to that is? When you're ready to get rid of it, since it's adhered so much stronger, it's harder to get rid of when you're done with it. So there's always a con and a pro to everything. So they're very stable under acidic conditions. They don't fall apart very easily, so they're really good at protection, but they're a little tough to get off. We'll show you how to get rid of them after. They have some other benefits that regular oxygen acetals do not have. What you'll notice and probably be thankful for is that the mechanism is exactly the same. Don't be scared by the reagents. We're just going to use a Lewis acid instead of a protic acid. So a Lewis acid like zinc chloride. You can pop one of the chlorines off. Okay, and now we've done our acid-base chemistry, check. Now we're ready for our nucleophile chemistry. The sulfur is what we're driving on. And we're going to do our in, up. O, I just start doing it as O zinc. It'll end up leaving after a proton shift, acid-base chemistry. dropped my hydrogen inadvertently, but this is going to leave. And we can push the electrons in. Now we do down and out. Here's my sulfur, down and out. We've lost the oxygen that we started with. Right, it's the same mechanism. Just using non-reversible arrows here. Sulfur is now double bonded. And we're ready for the in-up. In and up. And once this happens, the workup then ensues, and we have a thioacetal. Same mechanism. It's the same mechanism. Do not be concerned and worried about the zinc as an acid or the sulfur instead of the oxygen. Completely interchangeable. Now, this makes a thioacetal, which you can totally use as a protecting group. They're just a little tougher to remove. What's interesting, as an aside, I'm not going to test you on this, but for those of you guys who are interested, what I like about thioacetals is that they actually can be if you started with an aldehyde, you can deprotonate them. So here's your thioacetal. If you use a really strong base like N-butyllithium, really strong base, you can actually deprotonate that hydrogen. It's acidic enough to be deprotonated. What? You can't do this with acetals, the oxygen kind, but you can deprotonate that and then use it as a strong nucleophile. Okay, why is this interesting? Because let's call this carbon 1. Look at carbon 1. Tell me what charge it has. It's negative, right? This is carbon 1. What charge or partial charge does it start with? Because of the carbonyl, it's a positive, partially positive carbon always, right? Because of the dipole. This is called an umpalong effect. And what you're able to do is reverse the polarity of an atom in the molecule by changing its functional group. So by changing it into a thioacetal, you're able to deprotonate it because now that proton has a different pKa. You can't deprotonate the aldehyde at all. No way, no how, because a carbon plus is not going to make a good carbon minus. However, I don't have a carbonyl when I have a thioacetal, and that is well within the pKa range for N-butyllithium to abstract. So as an aside, you can suddenly make a carbonyl into a nucleophile. It's kind of an interesting synthetic strategy for some reactions that you might come across. Okay, I just made it an acetal that's with sulfur, thioacetal. How the heck do I get rid of it if it's non-reversible? Well, you have to entice it with a special type of acid. So zinc chloride won't do it. I'm sure it's no surprise that we're going to have to drive water back on. Okay? However, we have to entice the sulfur away from carbon. Therefore, we have to choose a Lewis acid that is stronger, makes stronger sulfur bonds than with carbon, and that is mercury. Unfortunately, no one wants to work with mercury, but that is one way to entice a sulfur away. If ever you're in front of a committee and they're asking you, in a thesis defense, hey, how will you drive the sulfur away? Just tell them, I'll just throw some mercury in there. Definitely thermodynamic bonds between sulfur and mercury. Now, how is that going to happen? It is indeed the same exact mechanism with the mercury as the Lewis acid instead of H+. It's going to operate the exact same way that we saw for the acetals. I would like you to write this on your own for practice. I want you to have your hand at extrapolating this mechanism backwards. Remember, your product is going to be this. I'll give you the product, but I want you to write the mechanism on how to get to those products. Now, the last thing that I'm going to show you is another advantage. So in addition to being stronger, a second advantage for thioacetals is that if you make a thioacetal from a carbonyl, you can do a second reaction and completely reduce away the functional group like it was never there. It's sort of like hydrogenating a double bond. Remember H2 with some metal catalyst gets rid of the double bond like it was never there? Well, the carbonyl version of that, you have to work through the thioacetal, turn it into the thioacetal, and then you can hydrogenate it away with a special nickel catalyst called rainy nickel, but it's just H2 with some metal catalyst, goes away, poof. You can think of it like Sin4. It gets us there. It's not really what happens, but here's your metal surface with the two hydrogens, and you can see that the carbon gets a hydrogen, the sulfur gets a hydrogen, and you can imagine it forming, and then doing the same on the other side, so that you end up with the two hydrogens and your thiol. So you can use a Sin4. It gets us there. Is that really what happens? Not really, but it's a lie that kind of works.